Hey there and welcome back. We started talking about memory circuits, that is, capacitors and inductors have been introduced. And uh, in the last video, we quickly saw what the circuit behavior is to constant current and voltage sources. But now let's see what will happen if the voltage and current sources are time varying. So, mm, uh, just taking the simple RC circuit, RC in series with a source. Just that in this time the source is time varying, that is Vs of t is Vp exponential St. So what will happen? Starting with the differential equation only. So that is RC times dVc by dt plus Vc gives Vp exponential St. So on solving this differential equation, we'll get something like Vc of t is equal to Vp exponential St upon SCR plus 1 plus Vc of 0 minus Vp upon SCR plus 1, and this whole times exponential minus t by RC. And this is when SCR is not equal to minus 1. So what does this indicate? Vc of 0 was the initial voltage across the capacitor. The the voltage source is exponentially varying, and we have got two terms, that is the forced response and the natural response of the system. So, as you can see, the natural response does depend on the input as well as the initial condition. But the forced response, as you can see, is it is an eigenfunction of the exponential function exponent e raised to s of t. So, the special thing about exponential input is that the forced response is something a function of s times e raised to s of t. So once again, I'm saying that it is the eigenfunction, and the force response or the steady state response, as we say it, uh, is the transfer function times exponential s of t. Whereas where the transfer function is the function of s that comes out and is multiplied with the exponential function, that together makes the force response. So in this case, how to find the transfer function? Well, we know it. It is 1 by CR plus 1. But once we know that that the force response is going to be something, a function of h, let's say h of s and exponential st, we can just substitute it back into the equation and find the value of for this. So this is what the transfer function is. How it is an eigenfunction, and this was well when S is real. But what if S is imaginary? Let's say S is j omega, nothing will change. Everything will be replaced by exponential j omega t, and difference being wherever j omega t comes, we can always represent it in cos plus j sin omega t. Uh, and okay, this was all with the exponential essay response. But what if we now have something that is the input voltage is a sinusoid, let's say Vp cos omega t. Then, well, there are two approaches to this. First, going through the differential equation once again, and the other way being using what we just saw, that is uh, giving it an impulse response of let's say Vp by 2 times exponential j omega t plus exponential minus j omega. This is effectively cos omega t, but we just now saw how it behaves towards the exponential signal, so this might be easy to figure out. So what will happen? So for Vp by 2 times exponential j omega t, the forced response will be same Vp by 2 times exponential j omega t times 1 by j omega 1 plus j omega cr. Uh, this one being the transfer function part, and the other just because it was an eigenfunction. So the net force response will be the sum of these two, because the system we are talking of is linear, and on adding those terms we get yeah we get Vt times cos omega t plus omega cr sin omega t upon 1 plus omega cr whole square. And on further simplification using trigonometric methods, this can be simplified as given here. Another approach to solving this can be that we know that it is a linear system, so the uh, VC, the capacitor voltage, should be something times cos omega t plus something times sin omega t. There might come a phase difference of pi by 2. Uh, and taking these alpha and beta as constants to cos and sin omega t, putting them back, the VC value back into the equation, we can solve for alpha and beta, and the value turns out to be the same. Vp alpha turns out to be Vp by 1 plus omega CR whole square, and the beta value as well. So this was another matter. Now, and the natural response as well. Yeah, the natural response will be some constant as exponential minus t by RC, taking the constant alpha n and putting and adding it to the equation, we get the total solution. Reminding once again that the transfer function and all that was for the steady state response, that is the forced response. We had left the natural response part, so adding that again, we get the complete solution. And how to find alpha n? Well, alpha n can be found using the initial condition, put t equals 0, and from that we'll get the initial condition. Sorry, the alpha n value using the initial condition. So there is one more interesting way to find the response to cos omega t. That is, the system is linear. Okay, so using this linearity, let's say for cos omega t, we get the voltage y of cos omega t. For sin omega t, we get y of sin omega t. And for cos omega t plus j sin omega t, what should we get? It should be y of cos omega t plus j times y of sin omega t. And what is this? This is nothing but exponential j omega t. And what is that we want? We want y of cos omega t. So what is it? It is the real part. It is the real part of the forced response to exponential j omega t. And here comes another method to approach this. That is, mm, the forced response for the uh, sinusoidal input. That is the real part of h of j omega exponential j omega t. This was another nice method towards it, and this is what we mostly use when solving problems. That is just taking the real part of what it was for the exponential signal, and going ahead. Uh, this now tells us that a linear system, whatever it may consist of, resistors, capacitors, inductors, dependent sources, we in steady state can represent any voltage as a transfer function times exponential j omega t, where omega is the frequency of the source, and omega, and so same goes for the current as well. So, what the an important property of capacitor and inductor comes out here. That is, let's say the voltage across the inductor is h of VL Vs times of j function of j omega times exponential j omega t, and I is h of I Vs exponential a function of j omega t times exponential j omega t. Now the property of the inductor VL is L di by dt gives VL is equal to HIL Vs, a function of j omega t times j omega L uh, into exponential j omega t. On comparing these equations, we find that VL by IL, VL of t, IL of t, the ratio turns out to be j omega L, and for capacitor, it turns out to be 1 by j omega C. So effectively, j omega L is the resistance for an inductor, and effectively 1 by j omega C is the resistance for a capacitor. We can now um, use these values to treat both these elements as just resistances in our equations, and use something like the Ohm's law for dealing with them, the terminal quantities of these elements, and that will make the analysis much more easier. So as you can see here, uh, V of t upon I of t will be some impedance which will be complex, whereas the resistance initially was real. And now we can just use them, as I said, by resistances. We just replace the capacitor by a resistor of value 1 by j omega c, and so on go the calculations. Coming to the last part of this video, that is the phasor analysis. Once that we know that we are diving into uh, sinusoidal signals, mm, where we can represent them as, let's say, in general, Vp, the magnitude. exponential phi j, the phase, and exponential j omega t, the time varying part. The real part of this expression will be the real thing happening in the circuit. So exponential terms are just for our convenience. So once we know that we are dealing with sinusoidal systems, we won't write exponential j omega t everywhere. We will just use uh, Vp e exponential phi j to represent the voltage. That will be the phasor voltage represented by V bar, and the actual voltage V of t, it will be V bar, the phasor times exponential j omega t, and then we can take the real part of this. So this concludes this short video. In the coming video, let's further analyze the memory circuits, and let's see what more these circuits have got for us. So thanks for watching, and see you there.